Okay, in this module we are going to do a calorimetry calculation with a phase change. So let's take a look at a situation where we have an ice cube, and the ice cube is going to be deposited into some quantity of warm water. And we're going to do the calculation as to what happens here. Well, we know that if the water is warm and the ice is cold, that our heat transfer is going to take place between the water and the ice in that direction. And so the water is going to lose temperature and the ice is going to gain temperature. So we should see a negative number come for the calculation for the water, and we're going to see a positive number for the ice. The tricky part about this kind of a calorimetry calculation is that there's three different heats that we have to concern ourselves with for the ice. We have to concern ourselves first with the sensible heat of the ice itself. That is, how do we get from whatever negative temperature we are up to the 0 point? Then we have the latent heat of the ice to convert it from a solid to a liquid phase, and then we have a sensible heat again of the ice water. Okay, so we have these three things. Now, many students mess this up, and they try to use a temperature difference between the negative temperature of the ice and the positive temperature of the final ice water, and then add the latent heat in. Well, that's a problem because the specific heat capacity of solid water or ice is different than the specific heat capacity of ice water, and we have to consider ourselves with this latent heat in between. So we end up having to do a calculation of three different kinds of heat involved with this calculation. So when we do our calorimetry calculation, you're going to see us do this in three steps. Okay, let's take a look at first of all the sensible heat for the ice. That's going to be the mass of the ice times the specific heat capacity of the ice times the delta T of the ice. And if I'm looking at the delta T of the ice, that would be T2 minus T1, as it always is. But in this case, T2 is going to be 0 degrees C, and it's always going to be 0 degrees C for T2, regardless of what my starting point is, because it's only ice up to the 0 point. If it's at +1, it's not ice anymore, it's water. Okay, so we have that one. So we know that our latent heat of fusion is what's going to unlock our latent heat, and that's going to be the latent heat of fusion times the mass of the ice. And finally, we have our sensible heat of the resulting ice water after the cube is melted, and that's going to be mass of the ice, it's still that same mass, times the specific heat capacity of water, because now it's in the liquid phase, times delta T once again, but this delta T is going to be T2 minus T1, and T1 in this case is always going to be 0 degrees C because that's the temperature that the ice water starts out at. So our sensible heat for the ice is going to end at 0 degrees C. Our sensible heat for the water is going to begin at 0 degrees C, and in between those two heats we apply the latent heat. So let's take a look at what that looks like in an example. So 600 grams of ice at -8C is added to 4 liters of water at 20C. Find the final temperature of the water. And we're given some specific heat capacities and the latent heat of fusion of water. So let's first of all do the sensible heat of the ice. And if I do that, I'm going to have the mass of the ice times the specific heat capacity of the ice times delta T of the ice. And I can look at that as 0.60. Oh, yes, I'm given my specific heat capacity in kilojoules per kilogram, so I've got to take that 600 grams equals 0.6 kilograms, watch your units, times 2.1 kilojoules per kilogram, times, and my delta T in this case is going to be T2 minus T1, which is 0 degrees minus -8. Right? Don't mess up your minus and minus there. And so when I do that calculation, I get 10.08 kilojoules. All right, my next calculation is going to be the latent heat, and that's going to be the mass of ice times the latent heat of fusion of the ice, and that's going to equal 0.6 times 333, and if I work that out, it's 199.9, so let's just call that 200 kilojoules for the latent heat. Now I'm going to do the Q of the ice water, and that's still the mass of the ice times the specific heat capacity of water because it's melted times the delta T of the water, and that's going to give me a 0.60 times 4.18 times, in this case, it's going to be T2, the final temperature of the mixture, minus 0. And if I do that, I get a number 2.508 T2. And lastly, I'm going to have the Q of the water that started out in the glass, the warm water. That's going to be the mass of the water times the specific heat capacity of the water times the delta T of the water, and that's going to be 4 kilograms because 4 liters of water is equal to 4 kilograms. Once again, we're watching our units, times 4.18 kilojoules per kilogram, and my delta T is now going to be T2 minus 20 because my water started at 20 degrees. And so that's going to be 16.72 times T2 minus 20. So now let's put all those together into our calculation. So if I do that calculation, I add all those up, they have to equal a net of 0. And so our 10.08 plus our 200 plus 2.5, let's call it 2.51 T2, plus 16.72 T2 minus 20 has to equal 0. Now this becomes 210.08. Let's call it 0.1. And 2.51 T2 plus 16.72 T2 minus 334.4 equals 0. And we'll rearrange this a little bit. We get 2.51 T2 plus 16.72 T2 equals 334.4 plus 210.1. We get 19.29 T2 equals 124.3, or T2 equals 124.3 divided by 19.29 equals 6.5 degrees C. Now, if I do this calculation and I get an answer of 6.5 degrees C, that means that my water has dropped, my Q has been out of the water, my Q has been into the ice, and this is the final temperature at stability. Now, it's always a good idea to double check this calculation, so let's just plug that temperature in to this equation and make sure we get something close to 0. So it becomes 10.08 plus 200 plus 2.5 times 6.5 plus 16.72 times 6.5 minus 20, and that comes out to 0.625, and based on all the rounding I did, that's a number close enough to being the 0 that the net heat flow is supposed to be to give us a good result. And so we've now done this calculation with the phase change in calorimetry, and it's just have to watch out for that little trick about making sure to do this piecewise, the ice, then the latent heat, then the water component.